My name is Lolita Amann. I'm a data scientist at Software Competence Center Hagenberg, and here I present the knowledge graph for causal analysis of industrial processes. The objectives of our framework are an analytical interface that closely cooperates with process experts. This includes a flexible choice of what is analyzed. This can include different process steps in a framework. It can also be actually different use cases. It includes on-the-fly evaluation of analytical steps and then adaptability based on these evaluations. It is important that the analytical methodology that is transparent and computationally efficient. So usually if there are analytical interfaces for the user, what is happening behind the scenes is kind of a black box. The user can only look at the output. Here, the user can interact at every step of building the model. The output of the model includes answering questions such as what input settings cause the target state observed, how will the target state behave if I change the input settings, and what are the smallest changes necessary for target values to increase or decrease. Here you have an overview of the functional structure and units that this framework comprises. It starts with the option to load data from Karen or also as a CSV and to visualize the data. You see an example on the left side. Based on this visualized investigation of the data, the user can decide whether he wants to include some time series or not in the model. These time series which are included in the model are then used to build a causal temporal structure, such as on the bottom right of the graph. And then this structure is exploited for Bayesian inference. This includes root cause analysis, what-if scenario testing, and forecasting. Bayesian inference can be sped up a little bit, which increases the usability of the tool by discretizing the data. We do use Gaussian mixture models to do that because it preserves frequency distributions in the data, which makes Bayesian inference way more reliable in the consecutive steps. Here is a more detailed overview of the framework. I will not go into detail, but you can pause and study this graph if you're interested. So you have loaded your data, you've chosen the causal pairs that you think are interesting, and now you want the model to build your graph. Now usually when you have different variables or different time series, you will encounter two kinds of relations between these variables. One are simultaneous relationships, which we identify with Pearson correlation, Spearman correlation, and Euclidean distance. And you will encounter delayed causal relations, where one time series influences another time series, but with a delay. We apply Granger causality, which essentially asks if the past of a variable A helps improve the prediction of a variable B, A Granger causes variable B. What we get as an output here are causal directions between variables, and we get a lag size that informs us how quickly a variable reacts to changes in another variable. So the graph that we retain has edges that give us the causal directions. In case of simultaneous variables, this is given by process expert and process flow information. And the edges also give us information about the statistical approach with which we have retained them. The nodes give us information about the variables themselves, their lag size, in affecting other variables, and the suitability of the data for range causality. Here, all nodes are green, which says that the data satisfy the assumptions for range causality. They can be read indicating that these edges might not be as trustworthy as they could be. So now we have our data and we have our knowledge graph, or also our causal temporal graph. The two together allows to retain frequency distributions for all possible cause configurations of any node of choice. And this is a prerequisite for Bayesian inference, which we perform using variable elimination. Now, variable elimination works way better with discretized data. I've mentioned that earlier. On the right, you see how we discretize the data. So we have clusters from Gaussian mixture models. The cluster means indicate the sort of then category labels that we get from this, and all data is, or all observations are assigned to either of them per variable. Once we've done that, we can perform root cause analysis of a process state. So if we encounter really low quality in some target variable, we can check what input settings were associated with it. We can do what-if scenario testing. This can be useful if you have a sensor that failed suddenly. You can put in your current configuration and see how, given these settings, what you would expect in this sensor, and you can have short-term forecasts. This is a rough overview of what you can do. Now, to see what you can actually do with it, there are two other videos, one on the ADAP use cases, where we use this framework to predict aeration success, and then we have it for the Veralia use case, where we describe how we use it for the Fiedler line. Thanks for watching.